All right, let's get started. It's my very great pleasure to introduce today's cloaking speaker, Professor Jordy Bouwman of CU Boulder. Professor Bouwman got his master's in chemistry from the Free University of Amsterdam. He did his PhD in astronomy at the University of Leiden in the Netherlands on the topic of spectroscopy and chemistry of interstellar ice analogs. He then had a postdoc in Berkeley before going back to Leiden for a little bit. There he won the Venny and Vitti Awards before he could win the Vici Award as well. We recruited him back here to the US at CU Boulder, where he's been since then. Jordy is an expert in lab measurements and quantum chemistry, so theory and experiments both. His specific overall interest is in astrochemistry, with particular focuses on carbonaceous molecules in the ISM, so the origin of complex organics for early life, among other applications, as well as origin of complex organics in the solar system, as well as hydrocarbon chemistry in general, particularly with application to Titan. And that's what we're going to learn about today. Take it away, Jordy. Thank you.
Well, thank you for the wonderful introduction. And it's a great pleasure to be here. Thanks for the invitation. I had a great day talking to many of you today, and it was also wonderful to see the facilities over here. So thanks again for the invitation. So what I will talk to you today about is the formation and dissociation of hydrocarbons in space and planetary atmospheres. And then, as Sucrit mentioned, I mostly focus on the laboratory approach, and then we mix in quantum chemical calculations to really get a molecular understanding of how those processes happen. But then last night, I felt like, there's something missing. I should mix in something new, something exciting. So I decided to work until 3 a.m. and still get a part of the presentation done on the latest results that we obtained on the dust accelerator that we have at the laboratory at last. So anyways, it's sort of going to be a threefold presentation with a lot of physical chemistry, a lot of experimental science, but bear with me so you can understand these conclusions. Now, before we get into the experimental details and drawing those conclusions about how those complex hydrocarbons form and dissociate, let me first put it in a proper context. So we know that these large hydrocarbons are present in space because we can observe their infrared emission bands. So this is work that was done by my PhD co-advisor, Lou Alamandola, who was working at NASA Ames. And they figured out that aromatic molecules, or these emission bands that you see in space, resemble the Raman spectrum of car soot. So they made a link between car soot coming from a car exhaust and these emission bands that you observe in space. And it led them to conclude that these large hydrocarbons are also floating around freely in space. And then they get excited by the interstellar radiation field. And as they cascade down to the ground state, they just emit these vibrational normal modes. So these are all just the normal CH stretch modes and CC modes and CH in and out of plane bending modes and so on that we know for large organic molecules or large PAHs specifically. Now, based over the years, based on these emission bands, people have derived that up to 10% of all elemental carbon is locked up in these molecules. So it's clear that they must play an important role in the overall organic cycle of organic matter. Now, people believe that these are formed in outflows of carbon-rich stars, but those stars turn out to be too cool to pump this IR emission, and therefore you can't really point out where they are exactly. So what my research group aims to do is to understand by which mechanisms these PAHs, the polycyclic aromatic hydrocarbons, form in the interstellar medium. Now, they're not only of interest as this class of molecules, but it turns out that when you sort of dissect one of those regions in space, so this is a photon-dominated region, and when you look at these PAH emission bands as a function of distance to a star, what you see is at a large distance, you see 70 micron recorded by Herschel, which is just effectively the black body radiation coming from warm dust. But as you get closer to that star, you see that the spectrum changes. So the spectral decomposition. So green is mostly the 6.2 micron band that starts to grow in. And as you get even closer, then 2 indicates that you get emission from C60. So people then started to think that, well, you get closer and closer to the star, and it seems like these aromatic molecules get photoconverted into C60. So you can ask yourself the question, by what sort of mechanism is that then happening? And then astronomers then say, well, okay, it's just you start off with a planar PAH, and it's a large PAH because only large PAHs can survive in space. They must have sufficient heat capacity to have a lifetime that's long enough to irradiate the energy down again. But then, you know, this is an astronomer talking chemistry, because this is clearly not the way it goes. So what we are interested in is exactly understanding what the underlying isomerization mechanisms are that drive the formation of these pH derivatives, or these fullerene-like species. Then very recently, say over the past decade or so, people started to really focus on these organic or PAHs in space, but then to try to uniquely identify these aromatic molecules. So far they were only observed as a class. You know, you see these emission bands, but they're all broad emission bands, because all of these aromatic molecules have the same IR spectrum effectively. But then people started to do radio observations to try to figure out if we can actually identify aromatic molecules. And the first aromatic molecule was benzonitrile. It's not depicted on this slide. But then later, people also realized that there's cyanonaphthalene, but also these other, well, they're not PAHs, but this, well, you can call this a PAH. It's aromatic and it's a polycyclic molecule. But anyways, this zoo of all these interesting molecules is starting to grow bigger and bigger. So not only do we know that there's this large class of molecules, the aromatic hydrocarbons that we see as a class, but we can also see them as these individual species. Now, the one that, this is all, by the way, measured in Taurus molecular cloud, TMC1, which is a cold region in space. So the temperature is about 10 Kelvin, very cold. And the densities are very low, say 100 or maybe 1,000 molecules per centimeter cubed. So what this tells you is that to get to this sort of chemical complexity in a region like that, you really need to have specific reactions that may be driving this, right? So you need to think of reactions that are going over no barrier. But not only that, they also need to go down the hill and end up somewhere. And they need to be able to get rid of their energy. So typically they're of the addition elimination type. So you add something to your radical, and then the reaction happens, and then it sheds a hydrogen atom or a methyl group or whatever. So those sorts of chemical reactions must be driving this if it goes in a bottom-up fashion. So there was a big debate in the literature. Do we build up molecules from scratch, from the elemental composition, or do we even dissociate these larger aromatic molecules, giving rise to these species? So we are interested in figuring out how under those interstellar conditions in TMC1, you can form these complex hydrocarbon species. And then there's a specific focus on this one. So this one is called orthobenzene, which is a funky species. It's a biradical molecule. And I sort of had this impression that it may be a key player. And as you will see today, it turns out to be a key player in formation of those complex hydrocarbons. Now, of course, this is maybe closer to home for you. All of these types of reactions also play a role in atmospheres like Titan's atmosphere, where we know that this photochemical haze is formed. So Cassini-Huygens mission gave us a great view on what's happening in the atmosphere. And we know that all of those complex hydrocarbons form, again, despite the very low temperature of about 90 Kelvin. So we're still looking for reactions that can explain how those complex organics form. And then also specifically, my group is interested in trying to figure out how you can incorporate those nitrogen atoms in these complex hydrocarbons. Now, the way I do this, and what I will show you today, is an overview of the research over the past decades. And then, well, first I will show you how we can study the formation of PAHs in complex hydrocarbons using synchrotron radiation. So I will take you through this process. So this is the Swiss light source, the vacuum ultraviolet beamline specifically, that makes radiation tunable between 5 and 21 electron volts. And this is perfect radiation for soft ionization. So when you do time-of-flight mass spectrometry, you can gently ionize your molecule, and based on photoelectron spectroscopy, as you will see, you can make identifications of which products are formed from the reaction under investigation. Now, in the second part of my talk, I'll just give you one example of how you can study the dissociation of aromatic molecules by making use of radiation from a free electron laser. Now, this specific instrument is at Radboud University Nijmegen, and it gives you radiation in a fingerprint region of the IR, so 5.5 to 60 micron, but it's so intense, it goes up to 120 millijoule per pulse. So for those of you who know lasers, that's a lot of radiation coming from an infrared laser. And we can make use of that extreme pulse energy to investigate products formed in an ion trap time-of-flight mass spectrometer. And then the last part, so this is what I had to add last night. I was like, I need to advertise this dust accelerator to you, because here we recently got a paper published where we accelerate dust particles and we look at the detectability of these dust particles in interplanetary and interstellar dust particles. So we're trying to figure out if we can detect organic molecules in those hypervelocity dust particles that we can detect in our own solar system. So I'll just take you through these 3 steps. And then, of course, starting on the left-hand side with the formation of PAHs from radical reactions. And so we're using this beamline, we're using a tunable VUV radiation to gently ionize our molecules. And we do that in a system called the I-square PEPICO apparatus. So it's the imaging squared, so 2 imaging plates. You can image electrons here, you can image ions down there. And then it's photo-electron, photo-ion coincidence spectroscopy. What we do is we couple that system to this pyrolysis reactor. A pyrolysis reactor is basically just a silicon carbide tube that you can heat up. By heating up the material in that silicon carbide tube, you can just generate radicals by pyrolyzing a radical precursor. Now, if you then co-flow that radical precursor with a reactant, you can just make your chemical reaction happen inside that hot tube. So you just crack your radical precursor and it reacts with a co-flowing reactant. And then the products exit the tube on this side. They go through the skimmer and enter the detection chamber. So what happens in the detection chamber is that the radiation from that Swiss light source, so your species goes there, radiation from the Swiss light source hits your species, ionizes it, creates a pair of a cation and an electron. But then it's in an electric field, as you can see. So what's happening is that that field is just going to move the electron up while the electron is light. So it just hits the detector almost instantaneously. And it sets the time 0 for your time of flight measurement. So you measure the arrival time of the electron, start measuring the time of flight of the ion, giving you the time of flight and thus the mass to charge ratio of your corresponding ion. Now, this is not all, this would be just basic mass spectrometry, but then in coincidence fashion. But the beauty of this particular system is that we do imaging. So instead of just having an electron hit that detector up there, we also have information about the position where the electron hit the detector. And therefore, you can only consider the electrons that have 0 kinetic energy. So you only correspond or you only find coincidences with this ion and electrons that sit right in the center of your detector. Those are the threshold electrons. And when you look at how those correlate with the ions, you can construct what's called a threshold photoelectron spectrum. And these threshold photoelectron spectra give you a lot of information about the isomeric products that you formed in your reactor. So not only do you have information on the mass to charge ratio of the product that you form, but you also have a photoelectron spectrum that allows you to identify which exact isomer was formed from your reaction. Now, again, the interesting part of what was detected in TMC1 was orthobenzene. Orthobenzene is a peculiar species, biradical character, so it must be very reactive. The column density in TMC1 was pretty high, so it must play an important role in the overall chemistry. So then I was talking to this professor at the University of Würzburg. So the professor is called Ingo Fischer, but his graduate student synthesized benzocyclobutanedione. And they realized that when you heat it up, it just decomposes very cleanly into orthobenzene and 2 carbon monoxide molecules. So when you heat it up, you get cleanly your orthobenzene and 2CO, but they were only interested in the spectroscopy of that orthobenzene. So I said, well, if you don't mind, can you leave some of that sample? I'd love to study it. And then we decided to just measure a bunch of reactions involving orthobenzene. So we measured the reaction with closed shell hydrocarbons, C2H2, C2H4, C4H6. So this is work, some of it is published, other papers are still in preparation. We reacted it with a resonance stabilized radical, allyl, C3H5, and we reacted it with methyl. And just in view of time, I just want to give you a flavor of what it is we've done over the past years. I'll only show you the reaction of orthobenzene with methyl, also because it has great implications for what's happening in the interstellar medium. And again, keep in mind that what I'm saying now does not only apply to the interstellar medium, but these reactions are also driving the formation of complex hydrocarbons in an atmosphere such as Titan's atmosphere. So I'll show you the reaction only with methyl in this case. And of course, we use this I-square-PEPICO spectrometer. So we can do mass spectrometry, and that's what we do first to convince ourselves that we know how we pyrolyze a radical precursor. We know how we pyrolyze the precursor for methyl, which in this case was acetone. So here I show you a mass spectrum recorded at 9.5 electron volts photon energy at the beamline. And you can see that when we pyrolyze this benzocyclobutadiene, so this precursor for orthobenzene, we can see that we cleanly form mass 76, which is orthobenzene. So you can record the threshold photoelectron spectrum and convince yourself that, yes, this is just orthobenzene. There's no ring opening. There's no other funny stuff happening. And there's almost no bimolecular chemistry. So maybe there's some contamination that was left over from a previous experiment, but it's nothing we have to worry about. The next step is then to also introduce a radical precursor for the methyl radical, which is acetone. But first we did a run with just acetone to make sure that we also have the acetone chemistry under control. So that's shown over here. So here we pyrolyze acetone flowing in argon. So it's not shown, but this is just a trace amount of acetone flowing in argon at a temperature of about 1100 Kelvin. We ionized it at 9.5 eV. And here you see that you see methyl. So even though we ionized at 9.5 eV, and the ionization potential of methyl is at 9.84 eV, so we ionized our species below the ionization potential, you still see a peak at mass 15. So if we would ionize at 10 eV, it would go through the roof. So we make abundant amounts of metal radical. Now here, the other stuff, you can easily see that this is, well, leftover acetone, mass 58. There's some ketene over there. There's some acetyl radical. So we can understand all of the chemistry happening. And again, there's nothing we really have to worry about. We just need to acknowledge that those species are there, and we need to make sure that they don't contribute to the reaction that we're interested in. The next step is, of course, to mix in both of these radical precursors. That is the precursor to our orthobenzene and the precursor to our methyl, and then look at the differences between the two spectra. Now that's shown over here, and you see the same peak of methyl. Well, it's slightly smaller. It's probably because the temperature is slightly lower, slight deviation from the previous conditions. But all of the other species, you can recognize them. And then you see the only difference is over here, and that's mass to charge 90 and 91. So those mass to charge 90 and 91 species are exactly the products that you find when you directly add methyl to it, forming methyl to orthobenzene, forming 91. And then upon elimination of a hydrogen atom, you form mass to charge 90. So we know that these are the products that you form from this reaction between a biradical and your methyl radical. So we want to zoom in on this and then make use of the power of that synchrotron, right? You want to make use of the tunability of your soft ionizing radiation to figure out what the contributions of various isomers may be. So the first thing we did is we looked at mass to charge 91. So that's the reactive intermediate when you directly add your methyl radical to your orthobenzene. And we tuned through the frequencies of this beamline by looking at these ions that are coincident with zero kinetic energy electrons. Meaning you ionize your molecule, and every time when you hit a vibrational resonance, only then you can create electrons that have zero kinetic energy, right? So you tune through your frequency, and then when you hit this energy, then you can form one of those resonances. But of course, when you measure this in the laboratory, you better also find a way to simulate it. So what we did is we just took the structure of, this is a benzyl radical, You can, oh, sorry, there shouldn't be a dot there. There should be just plus. This is the benzyl radical ion. And what you do is you just make a Frank-Condon simulation of the overlap of the wave functions in the ground state here and the wave functions in the excited state for the cation there. And when you do those Frank-Condon simulations, so those are shown in purple here. So the intensities are just the stick diagrams. You can convolve that with a Gaussian that just replicates sort of the response curve of your beamline. You know, there's a limited resolution to the beamline. You can see that you can actually understand exactly how that ionization happens. You can convince yourself that this is indeed your benzyl radical that is formed as an intermediate for this reaction. So this is the power of that PEP ecosystem, right? Where you can really get information about the exact isomer that is contributing to the channel mass to charge 91. Now, of course, the next step is then to not look at the direct association product, but look at the addition elimination product. So that's a product of C7H6 composition. And that spectrum looks different, but again, you can pick up nice resonances here. There's clearly resonances happening, but it may be slightly more difficult. And this was particularly very more difficult because this turned out to be a bunch of isomers. So these are a bunch of isomers that you just cannot buy in a jar. So we needed to take a sort of a D route, and it was really difficult to actually analyze this data. So it took us 3 years and another paper before we could analyze it. But what we did in the meantime was just base identifications on newly measured reference spectra. So this was somewhere in the pandemic. We managed to record spectra of these species by using some funky lactone radical precursor. But then we could actually measure the exact ionization energy of each of these species. And I will spare you the details. If I do that, then I'll be just talking about this. So trust me, you can ask later if you want to see the details. But you can see how important it was to measure that exactly, because this ionizes at 8.27 eV, and this ionizes at 8.23 eV. So there's a super subtle difference between two of these isomers, but we had to discriminate between those two because these make up exactly the ionization resonances that you see over there. So the slightly shifted ionization resonances. But based on these spectra that we got from the other publication and their Frank-Condon simulations, we could really figure out which are the isomers that contribute to this photoionization spectrum. So we know exactly what this intermediate is, the benzyl radical, but we also know that we formed these 3 products from our reaction. That's all great, but of course, I'm a physical chemist and I want to understand, but I don't just accept the fact that I see 3 species. I want to understand, can I rationalize that I see these 3 product species? Why don't I see, for example, the tropyl radical that's shown over here? Why do I only see the benzyl radical? Why do I not see 5-ethynyl cyclopentadiene, but why do I only see these? Well, and that's of course clear when you do these potential energy surface calculations. You can scan all the reaction coordinates. You can figure out which products form over submerged barriers. That's these 3. The barrier is below the entrance channel of the reaction, whereas this one is formed over a barrier, so it's not going to compete with the other products. So we can rationalize the formation of the isomers that we detected, as well as the reactive intermediate. Now, this is one thing, but then still to go one step further, you should also do transition state calculations. So you can calculate the rate at which you cross all of these barriers as a function of energy, as a function of internal energy. And then when you take the relative rates at energy of 0, which is the energy of the entrance channel, you can estimate what the branching is over the various products. And from that, we plug those branching fractions into an astrochemical model to see if it makes sense with the observations. Now, this got published in Nature Astronomy last year, and we were very proud of it. But it would, of course, have never made it to Nature Astronomy if it would be just this story. So what we did is we reached out to Chris Schingeldecker, who's in Kansas, And what he did is he took our branching fraction and he calculated a rate for the reaction. He plugged it into his TMC1 model. And then we figured out that you get very close to the observed abundances. So where people before had no clue how you would form those complex hydrocarbons, how you would form those species with these 5-membered rings, then this orthobenzene turned out to solve everything in one go. But also it changed our view of the chemistry in TMC1, because I told you before that people were still arguing, is it top-down chemistry, is it bottom-up formation? But this is clear that this reaction is just driving the formation of those 5-membered ring species in a bottom-up fashion. So that's the conclusion of part 1. That is the reaction of orthobenzene plus methyl gives rise to these species that have all been detected in TMC1. So just by doing these one set of experiments, we can explain exactly how those species form. But then, not shown here, orthobenzene plus allyl also explains the formation of indene. So it's clear that orthobenzene is a key player in the formation of complex hydrocarbons. And again, we should also make sure that we extend this into planetary atmospheres. So I'm just presenting it in the form of TMC1, but you can imagine that it's broader, it has a broader applicability. That brings me to the second part of my talk, where I'll show you what we did. Well, I'll give you one example of what we did in terms of the dissociation of polycyclic hydrocarbons. And again, we used the free electron laser. But before I get into the use of the free electron laser, let me first tell you how we do this in the first place. So we study the photodissociation of these PAHs in their ionic form. That's the only thing you can do in the lab. And what you can use is an ion trap time-of-flight mass spectrometer. So this is an ion trap over here in the center of the chamber. Then this is your reflectron time-of-flight mass spectrometer. In this case, this is a dye laser. So this was still at Leiden University. So we had that system there, but the system was on wheels. So we could also put it in a truck. We could ship it to Nijmegen, which is close to the German border. We could connect it to this free electron laser and then conduct our experiments over there, making use of their tunable radiation. Now, what that thing does, that ion trap time-of-flight mass spectrometer does in detail is shown in this schematic. You introduce your aromatic molecule. It can be any sort of pH. We can ionize those pHs by either electron ionization or laser ionization, so laser multiphoton ionization. They always have a fairly low ionization potential in some intermediate states that help you along the way. But in many cases, when you ionize them, you don't just ionize them to form the parent ion, but you can also dissociate them. Now, in this case, there's some dissociation fragments, and we want to study the dissociation fragments, right? We want to see how the molecule decomposes and what the products are that are formed when you dissociate your aromatic molecule. So you need to figure out a way to maybe clean out the trap. There's a method called SWIFT, Stored Waveform Inverse Fourier Transform, that allows you to excite the secular frequencies of all of the ions that you want to kick out of the trap, while retaining the ones that you want to keep inside the trap. So you just design this pulse, which is just effectively just a Fourier sum, and you just excite everything you want to get out of the trap. So now you have your isolated photodissociation product. And the next step is to come in with the radiation from Felix, from the free electron laser, which is so intense that when you focus it onto the ion cloud, and when you resonantly excite a vibrational motion in your molecule, it will photodissociate. That's called infrared multiphoton dissociation. So you can make use of infrared multiphoton dissociation to figure out at which wavelengths this ion of interest in your trap is absorbing infrared light. So what it means is that if you do this as a function of frequency, you just construct a spectrum, right? You just look at the dissociation of your molecule as a function of frequency, and then you reconstruct your spectrum. So that's, well, of course, you kick out these ions, you expose them to light, you kick them out, and then you see the dissociation pattern for this ion of interest. And look at the dissociation yield as a function of frequency to construct your spectrum. Now, this was the first system that we studied, which obviously is one of the simplest pHs. It's a basic aromatic molecule called naphthalene. And it was interesting because in the literature, a lot of people did computational studies, but nobody ever managed to do any experiments to try to figure out what the species is that you form when you dissociate it. But clearly, when you go over these barriers, now this is called azulene, so you can make an isomerization from naphthalene to azulene, and then from azulene you can lose a C2H2 unit to form the species pentylene, or you can go to the right-hand side to form benzocyclobutene or phenylacetylene. But these barriers, these transition states, so the rate-limiting transition states, are very close in energy. You need to rely heavily on your computational method if you want to trust it. So we decided we now have this system, let's just photodissociate this naphthalene molecule and figure out what the actual spectrum is of the molecule that you form when you photodissociate. So that's what we did. We just exposed our naphthalene to an argon fluoride laser at 193. So we did multiphoton ionization, giving rise to the loss of the C2H2. And it turns out that it's a very gentle dissociative ionization process. Then we can swift isolate. So we can isolate that one product species over here that we're interested in by applying our swift poles. And then you can see that when you excite the other species in a trap, you actually enhance the signal. So there was sort of a metastable naphthalene cation floating around that collides with background helium and then gains enough energy to also go over the barrier of dissociation, which tells us that the internal energy of the naphthalene was probably very close to the dissociation threshold. And the next step is then to expose that isolated ion that we have in our trap to the radiation from the free electron laser and then pick up these dissociation fragments and then measure this dissociation yield as a function of frequency. Now that's shown over here. So here I show you the energy of the free electron laser in wave numbers and the dissociation yield on the y-axis. And then I compare this to B3 calculated spectra of the 3 possible isomers that people predicted using their quantum chemical calculations. So when you look at this, well, it's clear that the only species that has a good comparison with the measured spectrum is pentylene. So using this measurement, using this IR-MPD applied to the ions in our trap, we figured out that pentylene is the product that you form when you photodissociate naphthalene. And to get a full appreciation of what this means, you must realize what's in an ion trap. This ion trap maybe contains 10,000 ions. But then you isolate just this dissociation fragment, which is maybe, let's say, 1,000 ions. And even though you only have 1,000 ions inside your ion trap, you still manage to figure out what the product is that you formed from the dissociation of your parent species. I think this is always just fascinating, right? You can do super sensitive spectroscopy on a set of maybe 1,000 or a few thousand ions. Well, of course, there's an implication to this. So the fact that we now see pentylene is interesting. As I said earlier, that there's a connection or a possible connection between large pHs and fullerenes. And for those of you who know fullerenes obey the isolated pentagon rule, which means that every pentagon is surrounded by hexagons. Now, in this case, what you see is that this aromatic molecule dissociates and it forms 5-membered rings. So you can see that there's this facile formation of 5-membered ring species, even for the smallest of pHs. Now, of course, just measuring one pH doesn't allow you to draw any generalized conclusions, but it is interesting that this is happening even in this particular case. So what we did, this is just a conclusion slide. So this is what I showed you. So naphthalene isomerizes to azulene and forms pentylene by losing a C2H2 unit. But we also extended this to acridine and phenantridine, where we also showed, based on the same methodology, that you do include pentagons. So every pH that we tested so far seems to include these pentagons along the way as you dissociate them. And again, this gives you important clues as to how those fullerenes may actually be formed in space. And of course, we keep extending this. So we keep making larger and larger, looking at larger and larger molecules and try to see how those dissociate and what their role may be in the interstellar medium and in planetary atmospheres. Yeah, that then brings me to the final part of my talk, which again, I added last night at 3 a.m. So I hope it doesn't contain too many typos. And I think it should be okay. But anyways, I'll show you how we use this dust accelerator to measure, well, to try to characterize the detectability of organic molecules in interplanetary and interstellar dust particles. So this is it's called the Pelletron, this big thing here. And then this is our dust beamline. And then here at the end, this is called LEAL, which is the large experiment chamber. But you can mount any chamber on the end of this. So you can just come in with your own end station, or you can just use one of our end stations and then shoot these hypervelocity dust particles at whatever target you wish to shoot at. Now, this is hard to explain exactly how it works. So we have this little diagram over here that tells you how it works. And I would have a nice video, but in view of time, I don't show it. There's dust over here. That dust gets agitated. So it's dust of micro-sized particles. And we agitate it by applying by applying a periodic electric field that's going to just charge them up and throw them around, sort of. And then in that dust source, there's a needle that's set to about 17 kilovolts. And then when a dust particle hits exactly the tip of the needle, it's a very sharp needle. When a dust particle hits the tip of the needle, it gets ejected out of the dust source onto this line. So there's a couple of collimating plates over here, gets ejected into here. And this is the Pelletron, where we accelerate them typically to 2.2 million volts. So we can go up to 3 million volts, but 3 million volts, there's arcing, there's all sorts of trouble. So to keep this dust accelerator running in a stable fashion, we typically stay around 2.2 million volts. So those dust particles get charged up when they hit the needle and then get accelerated by that Pelletron. And then, of course, we need to figure out what it is we're looking at. So we need to characterize the dust in terms of its charge, its mass, its velocity, and that's done by these charge pickup detectors. So when a charged dust particle flies through this pickup detector, it creates an image charge, and from that image charge, you can figure out what the charge is of your particle. Of course, from the moment it enters and the moment it exits, you can already get the velocity, which is then refined by measuring it again. So you can measure between those two, and they're at a certain distance. So you can figure out what the velocity is of your particle. And based on that, you can also calculate what the mass is of your particle. But that is all done very quickly, because 2 meters later, 2 meters down the road, you want to be able to make a selection. You want to say, do I want this particle or not? So you get what you get. You never know which particle is going to hit your needle, but you do want to do measurements, for example, in a certain velocity bin of hypervelocity particles. So there's this particle selector unit over here that tells you this is a good particle. Yes, we take this. This is a bad particle. We kick it out. And then it goes to another pickup detector that allows us to nail down the velocity of the particle to a precision of about 0.05%. Before it hits the experimental chamber, where we can analyze the dust particles or do whatever to the dust particle that we want to do. Now, this is then what the paper that we recently got published was about. And, it's right up my alley. So it was anthracene. So anthracene is a C14H10 aromatic molecule. And we collaborated with Steve Arms and his postdoc, Dare Chen, at the University of Sheffield. They're a chemistry group, and they found that there's this polymer. It's called polypyrrole, and it's pretty useless. It's very brittle, and it's not of any use in any other application. But it turns out that you can very nicely synthesize this polypyrrole around your aromatic molecules. So these are just ground down bits of aromatic molecule that you can just get from Sigma Aldrich or whichever is your preferred vendor. And they found a way to immerse this in an oil and then coat it with this polypyrrole. Now, this is needed because all of this accelerator stuff that I've shown you is all based on electrostatic acceleration. So you need to find a way to charge your particle. An aromatic molecule or a cluster or just a crystal of your aromatic molecule cannot be charged. So you need to find a way to overcome this. So we synthesized, or I have to say Steve Arms and his postdocs synthesized these particles with a polypyrrole coating, which allows us to charge up these particles and therefore also fly them in a dust accelerator. And they managed to keep the coating of that polypyrrole down to 20 nanometers, so it doesn't have too much of an effect on the overall appearance of our particles when we detect them. Now, today I also saw interesting ways of coating materials. There's also various coating facilities at our dust accelerator lab. And we've been coating nano diamonds, nano rods, pieces of graphene, and we can just give them a silver coating or a copper coating such that you can fly them in the dust accelerator. Now, this is then what happens. We can characterize those dust particles. We can fly those anthracene dust particles, and we can characterize them in terms of their mass. So that's the mass on the y-axis. And we can characterize them in terms of their velocity. And then it also says particle radius, but this particle radius, of course, assumes a certain density of anthracene, and it assumes that the particles are round. So I wouldn't pay too much attention to that scale. But what you should take from this is that we look at sizes of about 40 to 1 micron approximately. But again, this is assuming a spherical model, which clearly, based on the pictures, they're not. But what you should take from this is that we start off at about 2 kilometers per second, right? So it's hypervelocity, very high velocity dust particles, but we can go up all the way to about 30 kilometers per second. And we can just do with those particles what we want to do. And what we wanted to do in this case is, of course, simulate what would happen if these organic molecules would be part of an interstellar dust particle. It would be detecting it with a dust detector on some space mission. Now, of course, to detect your dust particle on a mission, you must have an instrument. And the good thing about working at LASP is that people have been developing dust detectors over the past decades. So we got to use hyperdust. And hyperdust was shown over here. Hyperdust is of particular interest because hyperdust is in fact an IDEX prototype. So IDEX is the Interstellar Dust Explorer that is currently being mounted on the Interstellar Mapping and Acceleration Probe. So it's going to sample from the Lagrange point the interstellar and interplanetary dust particles. It's going to measure the time of flight mass spectra of those particles to see what the constituents are, to figure out what the building blocks of the solar system were. So this was particularly interesting because we can directly relate our findings in the laboratory to what you are going to find when IDEX does its measurements. Now, the schematic of the system is as follows. So you can see this surface area that has a diameter of about 40 centimeters. So this is where the particles impact. So the dust particles fly in through these grids, then hit the surface of this detector plate over here. And then the ions that are born, so they hit the surface at such a high velocity that you get dust impact ionization. And then the ionization, the plasma that you generate will emanate and then turns around because there's a parabolic grid at 3.5 kilovolts over here. And then it is parabolic because it's in such a way that you effectively just focus the ions down onto this dynode detector. Now you may say, okay, the resulting mass resolution is not too big; it's only 100. But that's it's a trade-off. This is an instrument that needs to capture also interstellar dust particles, and there's not too many of them. So you need to have a large surface area to be able to collect those particles, and therefore you sacrifice some mass resolution, but still it's going to give you compositional information. This is just some spectra that I want to highlight. So Becca, so we recorded about 1,600 spectra. And Becca Mikula, the graduate student who was the first author on this work, she randomly handpicked a bunch of spectra. And then we velocity binned those spectra, but she had to analyze every single mass spectrum individually. So we analyzed a total of just over 300 mass spectra. But just by the way the particle ionizes, you need to find time zero and your stretch parameter individually for every single mass spectrum. So it's intense labor. And she did a fantastic job getting this holistic view of how these anthracene particles then ionize and what sort of information it gives you. And what you see is, as long as you're in this 2 to 6 kilometer per second bin, this is on a log scale. So you can see that your mass to charge 178, which is your anthracene cation, your anthracene parent molecule, is very abundant. And then that's either 13C or there may be some protonated anthracene over there. But other than that, well, there's some fragmentation over here. And then the ones that stand out from the crowd are odd species. You see them all the time when you look at dust impact mass spectra. This is sodium and this is potassium. And somehow, because they're low ionization potential, they always show up very strongly. We don't worry too much about them. Main conclusion is, these low velocity conditions, you would see the intact parent ion. But then as you go up in energy, this is 6 to 10 kilometers per second, all velocity band. So this probably is the sum of about 60 mass spectra. Here you see, well, that's still your sodium and potassium, but now you see a bunch of hydrocarbon fragments, and you even see your carbon ion over there, just C+. So you see that the parent ion is much weaker, and you kind of start to see a trend over here. So at some point, you just enter a zone where you look at plasma chemistry. So you no longer probe the actual parent ion, but you look at the chemistry that's happening in the emanating plasma plume. And then, well, this is clear. This is all separated by about 12 AMU. So that's carbon chemistry. So this is just carbon clusters that form in your plasma plume. But you can see how critical this is in characterizing one of those dust instruments. So we know how to actually analyze the mass spectra and what the limitations are for analyzing organic molecules in such mass spectra. Now you can take it even further and then you see, well, it's mostly hydrogen, there's some C, CH, but then, well, this is no longer the parent. It sits around the mass of the parent, but this is all plasma chemistry happening. Now this is one important plot where you see how, as a function of velocity, you can detect your anthracene mass or the protonated anthracene mass. And then you can see that it makes up about 15% of all ion counts up to a velocity of about, say, 4 or 5 kilometers per second. So this is sort of the speed limit of where you can still detect your intact aromatic molecule. Now, those are the conclusions of this part 3. There's a speed limit for the detection of PAHs when you want to detect them in these interstellar and interplanetary dust particles. And at high velocity, it's just the plasma chemistry that really dominates and takes over and washes out the information on your molecular species. But of course, you need to keep in mind that that's not the only purpose, because still, based on those dust impact mass spectra, you can get insights into the chemical composition of your dust particle. In this case, it's mostly hydrogen and carbon, right? Because you look at the pH, but you can imagine that an interstellar, interplanetary dust particle is going to show all sorts of metals and other species that are going to show up in your mass spectra. And I want to just end by giving you an outlook. So we got one of those precursor science investigations funded for NASA. It's for Europa Clipper. And we're currently building up this new ice target system that's going to be connected to this dust accelerator. So we can connect the dust accelerator here. In the center, there's going to be a copper target with a layer of gold on top. And then we can do a reflection absorption infrared spectroscopy on our ice that is cooled by this closed cycle helium refrigerator. And we can expose it to dust particles while recording infrared spectra. And in the meantime, we can also look at the time of flight mass spectrometer that's connected here. So there's a linear TOF. So we can also look at the ejected ions that are generated when this ice target is hit by the hypervelocity dust particle. Now, for a spectrometer, we chose to cover 400 to 12,500 wave numbers. And we go this far to also match it with mice. That's the infrared. Well, I'll tell it later. It just escaped me. but it's to monitor. So mice is going to monitor the near IR portion of the infrared on the surface of Europa. And when you can monitor the near IR portion of the spectrum, while also knowing what sort of ice particles or what sort of ions are ejected, that's going to be extremely helpful for analyzing data coming from Europa Clipper. Now, of course, I don't have to tell you that there's a horrible environment at Europa because it's in the magnetosphere of Jupiter. It's going to irradiate it with electrons and ions and whatnot. And we're going to simulate that by using we decided on a 10 kilovolt electron gun. It's going to process those ices. So we have control over all of those conditions in our experimental system. And then the idea is, of course, that we have a cold sample. We can grow an ice on our cold sample under very, very nicely controlled laboratory conditions. So by making use of infrared spectroscopy, we can monitor exactly what the concentration is of the organic dopant in our ice. And then we can also expose that ice to a dust particle. We can see how our dust or how our ice erodes. We can hopefully also detect chemical changes in our ice by just looking at the formation of new chemical bonds that show up in the infrared portion of the spectrum. And well, of course, the goals are all related to Europa Clipper. So first being to monitor the survivability of organic molecules. So one of the big questions is when these fresh molecules from the subsurface ocean enter through the cracks and end up on the surface, how long can they survive over there under the conditions that are present on the surface of Europa? And we want to characterize the chemical reactions and identify the reaction products. And we want to be able to enable the identification of hydrocarbons using Europa Clipper, and then specifically using SUDA. So SUDA, the surface dust analyzer, is going to detect these ice particles that are emanating from the surface of Europa. And we sort of lay the foundations for making those identifications. So this is just an advertisement. If you're interested in using this dust accelerator or any of the end stations, just shoot me an email and I'll be happy to help you in the process. And that brings me to the acknowledgement. So I'd like to thank you one more time for inviting me. And then, of course, all of the people at LASP, John Fontanese runs the dust accelerator, fantastic guy. Zoltan Sternovsky is professor in aerospace engineering. We work together very much on the pH dust project that I've shown you. Henry Cardwell, my graduate student, building the ice target system. Becca doing the aromatic dust measurements. And then, of course, collaborators that were involved in the work here and then the other people that were involved. Thank you.
Thank you very much for that great colloquium. We have time for questions now. And if someone online would like to ask a question, please go, just please post and we can open it up. And actually someone online already has a question. So Lucy, if you wouldn't mind just unmuting and asking your question, that'd be great.
Oh, okay. Well, I've got a couple questions. When you say that the reaction of orthobenzene and methyl radical is barrierless, how, is it just an upper limit? Is it really barrierless? Could there be a small barrier? You just can't detect it?
Yeah, that's a good point. We did some complete active space calculations to convince ourselves that it is indeed barrierless. Mm-hmm. So really zoomed in onto the association of the two. And we found that there's absolutely no evidence for even the slightest barrier.
Okay, very interesting. So I guess they're two radical species. So
they are two radical species, yes.
Yeah. And one other question, you're doing these ice experiments. There are a lot of people doing these ice experiments now. How does yours, do better than others, such as, this one at Goddard, Ralph Kaiser has one. I'm just curious.
Yeah, that's also a very good point. Of course, I'm also from a lab where one of the specialists in the world on ice experiments was. So Harold Linnartz, who's also acknowledged here, yeah. My PhD advisor, yeah. Unfortunately passed away. Well, of course, the thing that we have to bring to this field is a dust accelerator. So we are the only ones in the world who can actually couple these ice experiments to dust and we can see what the dust is going to do to the ice in terms of its morphology, in terms of its chemical composition. I think that's key here. And then, of course, the electron gun is just going to help the case because it's process the ices in multiple ways. But I think the main selling point here is the dust accelerator that makes it really unique.
Sure, yeah, unique experiments. Thank you.
Thank you.
I have a question, Roger.
Yeah, fascinating talk. So I'll try to confine myself to just one question and one comment. So the question is about the dissociation of naphthalene. So you looked at dissociation of ionized naphthalene, but of course in the interstellar medium and Titan, it's going to be mostly neutral naphthalene. And do we have to worry about that?
Well, you could worry about it. I don't want to say you have to.
Well, the implications.
But in the upper
atmosphere, you're going to get the same kinds of products from ionized naphthalene as neutral naphthalene.
I think you might still get similar products, but I think I saw studies in the literature, but it's been a while since I read those. But it might be the case that in sometimes or oftentimes it might give you completely different distributions and different products altogether. But still, in Titan's atmosphere, in the upper atmosphere, it's mostly ion-driven reactions, right? So it's the ionosphere.
Yeah,
but I think that's also where, at least what I remembered from those models, is where many of the complex organics formed.
Yeah, there are complex organics formed there, but photodissociation of those complex organics is important.
And that's my point, is that if this naphthalene, ionized naphthalene, is present in the upper atmosphere, that it may convert into pentylene ions. But again, to answer your question, it may be different on the neutral surface, but I seem to remember that there was a paper that also dealt with a neutral dissociation, or dissociation on the neutral surface, which, well, I'd be surprised if it gives the same, but it could be comparable.
Okay, my comment was about the dust accelerator. And, you know, Cassini, when it ended its mission, it went through the atmosphere of Saturn at 30 kilometers per second. And one thing that I think it was 30 kilometers per second. One thing that it found was there was a lot of dust or particles, particulates in the atmosphere that were hitting mass spectrometers. And I don't know if anybody's done it, but somebody should compare what you've done with what the Cassini instruments are.
Yeah. Yeah, it was CDA, right? Cosmic Dust Analyzer.
That in the INMS too.
INMS also.
Yeah. And the instrument's called CAPS, which is supposed to be a charged particle instrument, but it measured all kinds of interesting mass spectra.
Yeah, the one thing we did do is, of course, there were also the flybys in the Enceladus plumes. Mm. And I was like, this looks so much like, there's this paper by Frank Postberg,
yeah,
where they show the high mass organic compounds, is what they call it, from the subsurface ocean of Enceladus.
Yeah.
And I was like, this looks the same.
Yeah.
And in essence, it does look the same. So many of the features are the same. But then when you start to look at the details of especially the low mass species, it's completely different. So there is still this plasma chemistry happening, but still I'm convinced that all those lower mass species, the way they describe it in the paper, it took me a long time to really appreciate it. But it does give you a lot of detailed information on what the carriers may be that are responsible for those signals. So also a very good point, and I think it's worth to go beyond Frank Postberg's paper and also look at the old data from Cassini.
Yeah, I've thought that for a long time, but anyway, great stuff.
Thank you.
I'd like to ask a question, if I may. So you talked a lot about carbon formation of hydrocarbon compounds in the ISM. One of the things that's really interesting for folks thinking about origin of life and things like that is nitrile chemistry, origin of nitriles. So have you looked into the implications of some of the work you presented, particularly in part 1 for nitrile formation networks?
Well, yeah. So we had a complete plan on how to also explain the ones with the nitriles. And then nature is just fighting you because it does know there's no good radical precursor for this. And for those of you who know the literature, oftentimes when they see, well, anything with a nitrile has a whopping dipole moment, it's going to show up in your rotational spectrum, right? It's rotational spectroscopy 101, scales with the dipole moment squared. So you're very sensitive to those nitrile species, but oftentimes they just say, oh, it's probably benzene reacting with CN radical, giving you benzonitrile. It's probably naphthalene reacting with CN radical, giving you cyanonaphthalene. I think personally that similar to the reactions that I explained, so the orthobenzene plus methyl, there's probably an orthobenzene precursor with a nitrogen in it that's driving the formation of these nitrile species. So it's definitely on my radar, but I have not been successful so far.
Then also just building off one more question, if I may, building off Roger's question also just a little bit. Kevin Zonley has proposed that early Earth may have undergone Titan-like phases in the aftermath of large impacts. Can we take the reaction networks you're developing here for the ISM and really just apply them to such to the planetary environment, or how do we need to modify it or prune those networks in order to apply it?
I would say that a reaction like the orthobenzene plus methyl is absolutely barrierless. Of course, we have not measured the rate. So the rate was just estimated by Chris Shingeldecker based on the polarizability of the species, I think. And I don't know, that's where his magic came in. So if you want to apply that, I would say we first need to know the exact bimolecular rate coefficient, which has not been characterized. Of course, the branching, there's an assumption in the branching that the only transition state that plays a role is the rate limiting transition state. So in principle, you would need to do full like multi-well, the full, what do you call it? A master equation solver on it to get accurate branching fractions out of it. But if you would do that, I would definitely say it's directly applicable to Titan chemistry or to other chemical networks.
We have other questions from the room or from online. If you have a question online, you can either unmute or post in the chat.
My question is related to your transition state calculation. So could you see, like, is it really barrierless, the reaction between those two, orthobenzene and the methyl, like checking carefully for how the charge densities are getting reorganized and things like that?
Yeah, so this is, this entrance channel, is that what you're worried about?
Yeah, the transition state, how accurate is that in your calculations?
Yeah, so I said the same thing when I answered Lucy's question, that we did complete active space calculations on this entrance channel to convince ourselves that there's no barrier over there. And then, of course, you can see that this is not the direct product, right? It's a summary of the service. But first, you just attach the metal to there, and then there's a hydrogen transfer that needs to happen before you reach it. So first, you go somewhere, and then you cross another barrier for the hydrogen transfer to go there. But that's going to be barrierless also. Well, it's going to go over a submerged barrier, I should say. That's barrierless is wrong, but submerged barrier. But the thing that worried people and us most, that we convinced ourselves that it's indeed barrierless. Does that answer your question?
Yeah, I mean, I'm trying to see, like, when your transition state calculations, how exactly you are, what path you are taking, the reaction coordinates that you are sampling to get the barrier or to see no barrier.
Yeah, well, the reaction coordinate here would be just a CC bond length, right? So that would be, so you start off from the complex, and then you just extend the CC coordinate, and then you realize it just hits an asymptote. And then you take those calculations along that path and you optimize it using complete active space to convince yourself that there's no barrier.
All right, let's thank our speaker again.